All right, moving into measurements and units. Most books that you see will cover this first part of this unit, or really all of this unit, at the beginning of the year. And the reason why I didn't cover this at the beginning of this course is because we don't use it until now. We're about to use it when we move into moles and stoichiometry, and so I move measurements and calculations to this latter part of the course for that reason, to make it match up with where we're actually going to use it, which to me just makes sense. Because I've found that if you teach it too early, people forget it by the time you actually need to use it. All right, so scientific notation. You should hopefully be familiar with this from your own schooling or other courses you've taught. Basically, you use to write really big numbers and really small numbers. So, for example, the mass of an electron is a really, really small number. Okay, but we can write it significantly shorter if we use scientific notation. 9.1 times 10 to the negative 31 grams, or kilograms in this case. So same thing for writing different things. So if we look at these, we see a pattern that there's two parts. Number between 1 and 10, that can't be 10, but basically something with a ones digit and a decimal. Okay, so we always put the decimal after the first ones digit. Okay, and then 10 to some exponent, and that's what moves to decimal. Okay, for small numbers like the mass of an electron, it's going to be a negative, and for big numbers, it's going to be positive. Okay, I don't know why that extra 4 is there, but 6.02 times 10 to the 23rd. Odd. Okay. All right. So just writing them back and forth. The way I do this, and the way I teach it is, you come and you look. All right, put the decimal right behind the first non-zero number. So 9.296. And then you just count how many times you move the decimal. 1, 2, 3, 4, 5, 6, 7. So 9.296 times 10 to the 7. Big number, it's positive. Okay. I do like to do comma separators and spaces like this just to make the counting easier. So once again, put the decimal behind the first non-zero number, it goes behind the 6. And then count the movement. So 1, 4, 7, 10. Okay, so this is 6.614 times 10 to the negative 10. Then this one, 3.4, where the decimal goes, times 10 to the negative 125. Okay, and this one, 4.21 times 10 to the second. Scientific notation, you can use it. I had one teacher that I did student teaching with who made every student write every answer in scientific notation, which I thought was kind of silly. Because to me, the point of scientific notation is to save time. And so for me, like when I start, like 421, I would write as 421 because it's just faster. But when I start getting into 100,000 and millions, scientific notation is much faster. And a much easier way for me to even think about it because that's how my brain works these days. But you can also go the other way. So just simply move the decimal how many ever times it tells you to move it. So move the decimal 8 times this way to make it a big number. Move the decimal 2 times. Move the decimal 6 times, but go this way. So that would put 5 zeros in front. 1, 2, 3, 4, 5, and then there's my 6th move. Same thing there. All right, so we can go back and forth. So that's scientific notation. So helpful, important. So moving on into significant figures. Significant figures is one of those things where hopefully you've been exposed to it, but it's one of those things I tend to find that chemists are the most concerned with, or people who are really into scientific research worry about these kind of things. But what a significant figure is, it's basically saying that the quantity of numbers in a measurement matters because it tells you how accurate it is. So, for example, if I say that a rope is 3 meters, it just needs to be closer to the 3 than to the 4 or the 2. But if I say a rope is 3.0 meters, then I need to be a whole lot closer to 3. If I say that rope is 3.00 meters, then I have to be even closer. And then if I say it's 3.00 meters, it's got to be like really, really close, within a millimeter. And so every time I add a number there, every time I add those zeros there, I'm adding what we call a significant figure, or a sig fig. and it is telling me how much more accurate and precise that number has to be. Okay, so we call them sig figs or SF. When I'm writing it, I usually write SF. When I'm saying it, I say sig fig. So like I said, they kind of indicate the measure of error, the margin of error, and then generally understood that the last digit of any measurement is going to be uncertain and requires some degree of estimation. Okay. The main way we use these when we do calculations, so that we're not implying a level of accuracy that's not really there. And so it's important that we use proper significant figures in our calculations. All right, so rules for figuring out what figures are significant, because not everything is significant. So first, any number that's not 0, automatically significant. Those are easy. Zeros are where it gets complicated. Zeros are significant if they fall between two numbers. So here they're significant, here they're significant. This one's significant because it's between the two numbers. Okay. If they are right of a number and right of the decimal, so these two numbers here are significant, but these zeros here are not. Okay. And then also if they are left of a decimal, I can write 200 and put a decimal on the end of it, and it makes these significant. But if I don't put the decimal on the end of it, the zeros at the end are not significant. That's the nitpicky one. So that rule can kind of catch people. Okay. All figures in scientific notation are significant. So 3.20, the 3, the 2, and the 0 are all significant. And any exact number, by definition or counting, has an infinite number of significant figures. So for example, like a dozen eggs is 12 eggs exactly. So you could say 12.000000, as many zeros as you need. And that's how many significant figures it would have. Okay? Or if something's exact, like 1 foot is exactly 12 inches. That 12, once again, would have infinite significant figures. Or 1 yard is 3 feet. Exact. 1 kilometer is 1,000 meters. Exact. Okay? If it's exact, then it has infinite significant figures. All right, so let's look at some examples. Okay, 478 has 3 significant figures because they're all numbers. Okay, 606.01, that 0 is between two numbers, so it's significant. So all 3 of those are significant. 0.8250, that 0 in the front is just simply there as a space holder for the ones place. It's not significant. But that 0 on the end is, because it's after a number and after a decimal. Significant figure rules, you just kind of get comfortable with them over time. The more you use them, the more comfortable you are with them. So this would have 4. 0.043 kilograms. These are not significant. This is behind the decimal, but it's not behind a number. Therefore, it is not significant. All numbers in scientific notation are significant, so all 4 of these are significant. And then 7,000, because I didn't put a decimal here, only 1's significant. So it's important when you're trying to be exact there that you put decimals on the end if you are, in fact, exact. Okay. So like I said, sig figs will just become more comfortable as you use them. Okay. All right, operations with significant figures. Adding and subtracting. You cannot have any more decimal places than the fewest that you start with. Meaning, okay, so 89.302 plus 1.2. Okay, so if I'm adding lengths, this one was a very exact length measurement. This one, not so much. So my final measurement cannot have any more accuracy than the lowest one that I started with. I only have 1 decimal place here, so my answer can only have 1 decimal place. Okay, so you just round it off to wherever you need to. In multiplying and dividing, it's not about decimal places, it's about significant figures. So once again, if I take the same 2 numbers, this one has 5 significant figures, because all the numbers are significant and that 0 is in between. And this one only has 2. So my answer can only have 2 significant figures, so I have to round it off to account correctly. All right, so let's look at some examples. So if I add these together, My answer needs to be rounded off to 0.3 at the end because I only have one number after the decimal here. Same thing here. I've got 2 behind the decimal and 3, so I've got to round it off at 2. Here I'm multiplying, so now I'm about significant figures here. So 1, 2, 3, 1, 2, 3, 4, 5. So my answer can only have 3. So round it off to 41.9. Same thing here. Got 3 sig figs, so 3 sig figs is my final answer. And then when you're doing scientific notation, once again, 3 and 3, 2 numbers after the decimal, 2 numbers after the decimal in my final answer. Okay, so that's what's going on with sig figs. Now, where people sometimes run into problem is when you get something like, let's say you had 123,000 was your answer, but you were only allowed to have 2 sig figs. Okay, people sometimes struggle with where to round that, or let's look at one that you can see here instead of me talking verbally. Let's say we got 11,254.3 as our answer in the calculator, but your answer could only have 2 significant figures. Let's say it was a multiplication problem for some reason. You'd have to round off all of these. So you'd be rounding off to only 2 sig figs. So it would be 11,000 would be your answer. Not 11. You can't lose these places. The numbers have to stay in their. This is a thousandth place. This is 10,000th place. The numbers stay in their place, but you still can round off left of a decimal. It's possible. So you would just simply say 11,000 would be the 2 significant figure answer. All right, and so that's how you use significant figures. So that's scientific notation, significant figures, and we're going to be using those as we move into the next 2 lessons on measurement and conversions.